All right, I'm gonna really quick go over simple harmonic worksheet one, number one. We're gonna save the other two problems for after we talk about rotational physics a bit. So let's just jump into this. I posted a video yesterday, kind of going through the proof of why how we determine the angular frequency of oscillation of a mass spring oscillator. So we're going to use that today, but I'm just going to kind of try to tie it all together on this worksheet here. So first one here is to sketch a position versus time graph for the mass for two complete cycles. Label the axes with scales. We can't really label the time axis here. This is a position versus time graph, so we have the x position versus time. First thing I'm going to do is plus a, negative a. Those are positions. The max amplitude, we start at the max amplitude, right? When we let it go, it goes to the left, slows down, comes up, back to the original position. That's one cycle. And then we'll draw the second cycle. I'm going to run out of room, but that's okay. Not a bad little cosine. So that's kind of where we've got one cycle. And there's the other cycle, two cycle, second. It's the two cycle. All right, first cycle, second cycle. All right, and then right below it, I'll just quick do the equation that describes this line. Position equals a cos omega t. All right, so we just get used to writing that. Again, omega t. You know, if you think about velocity times time, it's like position. Theta is angular position. It's an angle, right? Omega is a frequency. Cool. Part C, the force diagrams. All right, so this is always kind of fun to draw so we can see what's going on here. So I kind of wrote them backwards here, which when I wrote them on the problem, I realized it when I went to make up the answer key, but whatever. I am going to put the normal force and gravity on all of these, right? I guess it's frictionless if I didn't say so. It better be. Sorry for my poor handwriting. All right, so this is oscillating back and forth. In the middle, there is no actual force technically when it's at the equilibrium position. The spring does not apply a force. But when it's over here, the spring is going to pull it back this way, say Fs, and when it's over here, the spring is going to pull it back this way. All right, so whenever the position is positive, right? Whenever the position is positive, the force is negative. Whenever the position is negative, the force is positive, which is why we technically, spring force is a vector quantity equals negative k times x. And technically x is a vector quantity. So there's a reason why on reference sheets this will be bold and this will be bold, because this is literally, the negative sign is telling you the direction of that spring force vector. All right, and then it has us setting up Newton's second law here, so we can really use any one of these force diagrams to do that. We can simply say, okay, F net equals ma, the net force acting on it, and again, those are vector quantities too, that does matter, right? It's negative kx. I could use the vector notation if I wish, just to keep track of this direction, but usually we don't. We usually just write it as magnitude, so that might confuse you more than anything. Maybe I should just kill it. So A equals negative k over m times x. And then here's the beautiful thing for part E. All right, so part E. So I'm going to write this up over here. A equals negative k over m times x. So I can have that for this next little part. And this is awesome. You can simply say, this is a legal operation in physics and on the AP exam, right? For part E, using what we learned in class, determine the angular frequency. Frequency and the period of the mass, you can simply say omega squared is equal to K over M, because the constant in front of the position variable, when you solve Newton's second law for the acceleration, it's always the angular frequency of oscillation. You can literally just state that. You can, you don't even have to really state it. You can just, if you, any problem, if you set up, it oscillates. If you write Newton's second law and you solve it for the acceleration, whatever variables show up in front of your position variable, which could be x, y, z, r, theta. So we're not doing the pendulum yet, but turns out that our position we make an angle, theta, right? And we're not going to do that yet because it relies on torque, right? There's actually different versions of Newton's second law that says torque net equals I alpha. It may be causing nightmares already for kids that took AP Physics 1, but don't worry. This is simply, it's not that bad. We'll get there. But that's why we're going to stay away from that one, because we don't know torque yet. All right. There's this one that's a metal spring, right? And it basically says, okay, the force upwards is, the restorative force is negative beta times the vertical displacement, right? Something like that. And then you say, oh, okay, MA equals negative beta. And it ends up being the same exact thing as this. And you say beta y, so A equals negative beta over M times y. Y is your position variable. Beta over the mass is your angular velocity squared. It's repetitive. You can just do it. You don't have to prove it like we did in the last video. So omega squared is K over M, which means omega is the square root of K over M. All right. Omega equals 2 pi times the frequency. This is units of radians per second. All right. Frequency is simply 1 over seconds. The radians gets confusing, but this is cycles per second, I should say. It's cycles, complete cycles per second. So there's 2 pi radians per cycle. So that's, the cycles would cancel. So if you want to rearrange it, you can say the frequency of oscillation is simply omega over 2 pi. So in this case, it's 1 over 2 pi times radical K over M. The period is the inverse of frequency. So that's got to be 2 pi times radical M over K. I'm just inverting that whole thing. Okay, and that's it for that one. And that's pretty much going to bring to an end simple harmonic motion for us. We talked about the conservation energy of it a bit. We talked about that problem there. I'll maybe give you some stuff to read in one of the review books, but I think we're going to move on to rotational motion on Monday. All right. Well, talk to you later.